Okay, here's another RC response example, but this time we're trying to find how many microjoules of energy have been dissipated in the 12 kiloohm resistor 1.6 milliseconds after the switch opens. Okay, to do this, first we are going to want to find the voltage at this node when t is less than 0. And in this case, when t is less than 0, these switches are going to be closed. So first, we will redraw the circuit with the switches closed. So switches closed. And then we'll see that we can actually combine these resistors now. So to combine resistors in parallel, we add the inverse of each one and then take the inverse of the answer. So I've already done the calculation, so this will equal 10.2K. So we will quickly redraw it again with this new combination. And then we will see 10.2K. We will see that this is actually a voltage divider. If you don't see it, I'll quickly redraw it again in a way that you might be able to see it really quickly. Now again, since our switches have been closed for a long time, we can actually change our capacitor to an open circuit. So we can just get rid of all of that. And then, yep, I'll redraw the circuit really quickly to show you how it's a voltage divider. So here's our capacitor, and here's our nodes. So we can just flip these, and then might look more like something you've seen before. So the voltage divider equation is going to be V out is equal to R2 over R1 plus R2 times voltage in. And we will replace our variables with, in this case, R2 is going to be 10.2, so 10.2K over 10.2 or 1.8K plus 10.2K times 60. This is 60 volts right here. And then plugging that into our calculator, we will get 51. So our voltage at right here at A is going to be 51. Okay, so now that we know that, we are going to need to find our tau. And to find tau for a capacitor, it's going to be R times C. And this R is going to be the resistance. Oops. Okay, so I don't know what happened there. Okay, where were we? Okay, tau. So in order to find tau, we need to multiply the resistance that the capacitor sees with the value of the capacitor. And when t is greater than 0 at in blue at t greater than or equal to 0. And at that time, the switches are open. So I will quickly draw the circuit one more time. Or I will draw what we see when the switch is open. So we have the capacitor, the resistor, the 12K resistor. And that is all we see. The capacitor sees when the switches are open. So all we have to do is simply multiply 12K by 1 over 6 microfarads. Over 6 times 10 to the power of negative 6, and we get tau is equal to 0.002. Okay, so then we will write our dissipation equation, which has the form xt, the initial xt, e to the power of negative t over tau. So now we know our initial, which is what we got over here, and we know tau, which is what we found right here. So we are ready to write out our equation, which is, so v of t will equal 51 e to the power of negative t over 0.002 seconds. Because remember, tau has units of seconds. We can also write this as 51e and take the inverse of 0.002 to get 500. So we negative 500 t. So there is our initial velocity or voltage of this point when these switches are open. So now we can actually start answering the question. How many microjoules of energy have been dissipated in the 12 kilo ohm resistor 1.6 milliseconds after the switch opens? Okay, so all we have to do is we're going to use this equation, E, which is our energy, equal to the integral of P dt. Because we want to remember that energy is simply the integral of power. And we need the energy at 1.6 milliseconds through this resistor, the 12K resistor. So we need to remember what we have. We have voltage and resistance. And there's a formula for power for voltage and resistance, which is V squared over R. So we're going to plug that into our energy equation right here. Move this over. Plug that in over there. So we'll get E equal to V squared over R dt. But this isn't just V, it's V of t squared. So one thing we can actually pull out really quickly before we start plugging stuff in is we can pull out 1 over r. So just really quick right here, we'll get 1 over r v squared dt. So we'll continue down here. So E equal to 1 over r v, quickly just rewrite everything, t squared dt. So let me just shrink that really quick. Okay. So now we can we'll start plugging stuff in. So first, we'll get E equal to 1 over resistance of 12K, integral of our V of t squared, which is what we found up here, which is what we found right here. So we're going to plug that in, 51 E 500 T squared dt. Now, first we are going to throw this square in here. So 51 squared is 2,601. And then we can pull that one out. We can pull that out, and then it would look something like this. Actually, I'll do it step by step. So we get 1 over 12k, this, and then 2601 E5. Oh, and then we want to remember when we're squaring a exponent, we just multiply them. So this is going to turn into negative 1000 t dt. Now we can pull out this 2601 and divide it by our 12k. Divided by 12, 1, 2, 3, and we get 0.21, round that to 7. And we're left with e to the power of negative 1000 t dt. Now, I haven't wrote them yet, but we have to remember that we are trying to find the energy 1.6 milliseconds after the switch is open. So our parameters are going to be 0 to 1.6 milliseconds. There we go. So now we're going to find the integral of e to the power of negative 1000, which is going to be 1, 7. It's going to be 1 over 1000 e to the negative 1000 t 0.0016 to 0. Now we can pull this 1000, this 1 over 1000 out again, or this negative 1 over 1000 out again. And in doing that, we will divide this 0.217 divided by a negative 1000, and we get a really small number of negative 2.17 times 10 to the negative 4. And then we will do this part right here. So we will have e to the power of negative 1000 times 0.0016 minus 1, because e to the power of 0 is 1. And now we will just multiply this through to find our energy. So this multiplied by e to the power of negative 1000 times 0.0016 minus 1, and we get 1.73 times 10 to the power of negative 4 joules. And that is our energy for this equation. Or since it's asking for the microjoules, we'll just multiply that by 10 to the negative 6. And we get 173.2 round microjoules. Okay, so now we're going to find how long does it take to dissipate 80% of the initially stored energy in that 12 kilo ohm resistor. So what we need to do is we need to get the initial energy stored. So we can simply do that by doing 1/2 C, which is 1 over 6 times 10 to negative 6 times 51. This will get the total energy stored in the capacitor when it's fully charged. And if we do that, we get 2.16, or that's 2.7 times 10 to the negative 4. We will then take this number right here and multiply by 0.8 for 80%. So 2.17 times 10 to the negative 4. Yep, 4 times 0.8 to get an energy of 1.734 times 10 to the negative 4. Okay, so now we have this. We will make this equal energy equation, which is 1, 2, over 2, C, and V of t, which is this, this thing right here, which is what we found right here. So we will take that and go 1.734.4, or to the negative 4, equals the derivative, because we want to get the t from t to 0. And do 1 over 2. Actually, skip another step. We need to remember that e, like we did before, is equal to the integral of p dt. And remember that we used v squared over r, that's equal to p. So that's what we're going to do here. We're going to do integral of t to 0, or 0 to t, v of t squared over r. And then we'll continue that down here. We got 1.734 times 10 to the negative 4 is equal to the integral of t to 0 of 51 e to the power of negative 500, all to the all squared over 12k. Okay, and then we will simplify all this like we did exactly above to get 251 squared divided by 12k, you get 0.2167. And then remember that when we square an exponent, we multiply them. So this right here will all turn out to be, and we can multiple some of the stuff out. So pull out the, we did over here, integral of negative 1,000. Remember, this is pretty much the same what we did before, dt. And then we will take integral of this. Let me just move this over here. And then that will equal 0.217 integral of, oh wait, not that, this one over negative 1,000 e to the negative 1,000 t from 0 to t. Now we'll simplify all this, and we'll get 1.75 or 34 times 10 to the negative 4 is equal to negative 2.1675. All I did here is I pulled out this 1 over negative 1,000, so I took 0.217 divided by negative 1,000 to get this answer right here. And then we just do negative 1,000 t minus 1, because e to the 0 power is 1. And then what we're going to do is we're just going to multiply this through. Like so. Actually, we're not going to do that. We're going to divide both sides by negative 2.17 times 10 to the power of 4, negative 4. So we'll take our left side, divide it by our right side here to get negative 0.8. So we got negative 0.8 is equal to e 0 t minus 1. We'll add the 1 over plus 1. We get 0.2 equal e negative 1,000 t. And then we're going to ln each side. 0.2. The ln of 0.2 is equal to negative 0.16. So negative 0.16, 0.61 will round, is equal to negative 1,000 t. So we'll divide by negative 1,000. And we'll get a t of 0.0016, or 1.6 millisites. And that is our answer.